Okay then, so I'm considering now joint F. Oops, sorry. Joint F, and that has a vertical force which we know is 2.5 in compression, so 2.5 coming up in compression, and that gets distributed into Fg and Fc. So we've got some vertical component in Fc. If we draw this triangle here, we have bays are 3 meters across, so 3 meters across by 4 meters deep, and that means that this diagonal is 5 meters from a 3, 4, 5 triangle, or alternatively we could say that, let me just make that a bit clearer, that's 4 meters. So 4 squared is 16, plus 3 squared is 9, 9 plus 16 is 25, square root of 25 is 5 meters by Pythagoras, or just from the 3, 4, 5 triangle. We can establish that this diagonal line has a ratio of 5 quarters of the vertical component and 5/3 of the horizontal component. So we can say that Fc then is equal to 5 quarters times 2.5 is 5 halves, so 5 fives are 25, 8ths is the value of Fc, which is 3.125. Okay, well, 3 and an 8. Okay, so that's our value of the force in Fc, and we can see that Fc is a tension force for this all to balance. So we've got compression coming up here, so this must go in the opposite direction and therefore be tension. So that's 3.125 in Fc. And similarly, we can say that 3/5 of that force ends up in Fg in the horizontal component. So we have 3/5, that's the ratio of 3 to 5, the horizontal to the line of action of the force, that's 3.125. So we multiply that by 3.125, or 25/8 if we like. This 5 cancels with these 25, so we've got 3 times 5 is 15 over 8. So 15/8 is 1.875 kilonewtons. So we've got a 1.875 kilonewton force in our Fg. Okay, so we will now work through. I think the next one to look at is joint C. Let's put that up here. So joint C has a component CG, Fc, which we know, which is sorry, let me just put this is Fg is equal to that again, which we so we're looking at this joint here, so we need to consider this CA, which we know to be 0. So resolving forces at C, then we know that we have 25/8 here, and therefore GC has a vertical component where that is in the ratio of 4 to 5, so 4/5 of 25/8. Again, these cancel 1 and 5. So I'm looking at GC is okay. I won't let me do the vertical component first. I don't think I've done that the easiest way. FG, we can look at the horizontal component of that. The reason I say that is that we've actually got a load acting on here. So we've got an external load to consider at C of 2. So I won't do this one yet. I'll come back to that one, having done the horizontal load first. So I've got, I'm calculating this vertical load in GC, okay, and GC is 4/5, sorry, 4/5. So it's in the ratio of 4 to 5 times 25/8. So that's 1, and that's 5. So 4 5s are 20 divided by 8. So, and then, okay, I've done it again. Sorry. And okay, this time I'll do it this way. So I need to do the -2. So I need to take this 2 off here. So 20 divided by 8 minus 2 gives me let's divide that by 4, so I get 5/2 minus 2. 5/2 minus 2 is 2.5 minus 2, which equals 0.5 kilonewtons. Sorry about that. I kind of started doing that. I thought of doing it a different way and then came back to doing it the same way. So I've got 0.5 kilonewtons, and that is a compression this time, because so this is the force in CG, which is this one here, which is 0.5, and that's in compression. Okay. Now I can come and do CD, which is my other horizontal load at this point here, and CD is equal to 3/5, that ratio, times the force in that FC member, which is 25/8. Again, 1, 5, so that's 15/8, which is, so CD is equal to 1.875, and that is in tension. So CD is 1.875, so I have 1.875 here. Let's keep on top of these. That's 25/8 in FC, which is 3.125. FG was 1.875, and I've also got GC as 0.5. Okay, So I'm slowly working my way through each node and getting the loads by resolving horizontally and vertically at each node to give me these forces, and I'm relying on these ratios of these members as being 4 in the vertical, 3 horizontal, and then 5 along the diagonal. Okay, I'll continue to work my way through those, and we'll work out the loads in the remaining members in the next video.